Hello everyone, and welcome to our talk on evaluating semantic representations of identifier names in source code. This work has been carried out by Yaza Weinak, myself, and Michael Pradel under Software Lab in the University of Stuttgart. In this work, we have focused on identifiers. So it is important to understand why they are important and where they are used. In general, identifiers convey information and meaning about variables, functions, and other program elements. And in recent times, a lot of developers have started using them for different code understanding and code analysis tasks. Let's take an example of a typical name-based analysis. So you have a source code, you process them, and then you end up with a vector representation of such code. You pass it over to a machine learning or deep learning model, and then that model essentially learns a downstream tasks. A concrete example of this setup would be a bug detection task by Pradel and Sen, where similarly you have a piece of code, you process it, you come up with the vector representation, and then you pass it over to the model so it could distinguish between buggy and non-buggy code. In their work, they experimented with different type of representations, random vectors and learned representations. For random vectors, what they observed was that even though they learn enough, they are beaten by word-to-vec learned representations, and you observe a increase in performance. And this result is in line with the observation by other researchers, where they observed that learned methods actually are able to encapsulate more semantic information as compared to random vectors. However, there is no current work that can actually compare and measure the effectiveness of these approaches in representing semantic relations. Inspired by similar work in natural language processing, we have gathered developer assessments about relatedness and similarity of pairs of identifiers in order to actually measure this phenomenon. An example of the pairs extracted in the benchmark is provided below. From the table, what one can clearly observe is that identifiers actually share various different type of relationships with one another. In the first example, substr is actually an abbreviation of substring. Min-text and max-text are opposites of each other. So they have a varying degree of relatedness and a varying degree of value of similarity between one another. In this work, we focus primarily on two types of semantic relations, relatedness and similarity. We define relatedness as the degree of association between two identifiers. Minute and second are associated by the same domain, top and bottom are opposites of each other, and pad right and padding top are features of the same concept. Similarly, similarity is the degree to which two identifiers have the same meaning, where one can be substituted for the other without changing the overall meaning of the code. So substr can be substituted for substring and the meaning would remain the same. Similarly, if we replace length with size, the same concept would be represented. And one interesting thing for this example is that even though length and size are syntactically different, they are still conceptually same. In this work, we were able to actually generate 300 pairs with ratings which constituted of 488 different identifiers by surveying over 500 different developers. We surveyed them using Amazon Mechanical Turk, and some were volunteers. We came up with a pipeline to actually extract all of the pairs and get the surveyed ratings. So we first extracted candidate pairs from JavaScript, 150K dataset. Once we had candidate pairs, we passed them over to developers and extracted ratings using two different sets of surveys, a direct survey and an indirect survey. Once we were able to actually extract these surveys and ratings on a 5-point Likert scale, we further filtered the extracted ratings against different thresholds to actually capture only the values which gave us the highest inter-rater agreement. You can find more detail on all of this process in the paper. In order to test and measure this, all of these methods against IDBench, we computed Spearman's rank correlation on similarity ratings between two identifiers using cosine similarity. To that end, we had 4 different categories of methods: token-based representations, subtoken-based representations, AST, aware representations, and string distance methods. And we extracted similarity ratings from all of these methods for each pair and then computed a rank correlation for them. Now moving on to our first actual research question, that is how well can these models actually capture these ratings. So looking at relatedness first, we can clearly see that all methods have a strong correlation with the benchmark, with learned representations actually performing a lot better than string distance based methods, and FastX model actually doing a lot better with over 70% of correlation. However, when we move over to similarity, we see a strong decrease in the performance. And one interesting fact is, in some instances, actually string distance methods perform better than these learned representations. And only FastX models, the subtokens models, do marginally well. And this is actually pretty interesting, where we see that even though relatedness is something that these models are actually able to capture, similarity is something that they struggle with. Based on these results, we wanted to further investigate in which cases do these models actually work well and in which cases they don't. So we've divided the data into different subsets, and the first subset is abbreviations, since they are commonly used for concise source code and they are readily available in the code. For relatedness, what we can observe is that all of the models apart from FastX CBOW has a negative correlation when it comes to similarity for abbreviations. And this can also be attributed to the fact that the subtokens method actually rely more on syntactic use. And similarly, for similarity, the result is more in line with the previous results, where similarity is actually quite difficult for all of the models. But overall, all of the models fail to associate similarity and relatedness. The second subset of data is of opposites. Since they often occur in similar contexts, we argue that it would be difficult for models to actually distinguish similarity than relatedness. And as observed in this graph, all methods actually show a positive correlation with similarity, with relatedness. However, when it comes to similarity, all methods, apart from AST aware method, actually show negative correlation. And this can be attributed to the fact that AST aware methods actually rely more on semantic cues than syntactic cues as compared to this token and subtoken methods. Due to time constraints, I've only presented a handful of our experiments. In the paper, we actually try to observe these models in more detail, and we try to combine them in an ensemble method and we try to see if each of them can complement each other. There's more work in the paper, and you're always encouraged and welcome to go and have a look. Finally, in this work, we've tried to highlight the importance of learning varying behaviors of identifiers for better code understanding. We showed that learning approaches actually perform better than string distance based methods. They are able to capture relatedness pretty well. However, all of these methods struggle to capture the notion of similarity. And we believe that considering these ratings that we have developed and the behaviors that we have highlighted, one can train better representations that can be used to perform better code understanding tasks. And thank you for listening. Our work is available on GitHub, and feel free to ask us any questions.
Hi everyone, welcome back. This is the Q&A session for the paper titled ID Bench, Evaluating Semantic Representations of Identifier Names in Source Code. We have Mois Rauf here. He's one of the authors of the paper. As a backup, we also have Michael here, but he's promised that he's not going to be answering questions. So please pop your questions in the chat so that they can start answering them. In the meantime, while questions start appearing, perhaps I can ask one question that gets close to, kind of pulls closer to my kind of research interests. Have you explored the idea of applying some similar approach to test code? We have a very, let's say, latent problem in automated test generation where we don't know how to name our variables and our methods, etc. Do you think that a similar approach could be applied there?
As of right now, with respect to scope of this work, we didn't any the problems that we essentially highlighted, which is this notion of semantic is not well encapsulated by different embeddings, and we haven't applied it directly to a task such as this test generations. However, we tried on our own to these different bug detection tasks, and it turns out that embeddings are something that do have an impact. So if you instead have a random one, and as opposed to something that encapsulates the notion of similarity a bit better, you would see an improvement. So in theory, one can argue that an embedding or a representation that has that highlights this this notion of similarity and semantic similarity better would perform better. But at least for the scope of this paper, we did not apply for such a task.
We have a question from Jonathan Maletic. Did you take advantage of any tools like WordNet or a Thesaurus? Do you think this could improve your results?
So at least for this, so what we wanted to highlight from this work was that the current embedding representations or identified embedding representations, I should be more specific, as of right now, they do not or have they do not encapsulate the notion of similarity because they do not include these behaviors within identifiers. Fact that it is difficult for embeddings to differentiate between abbreviations, which in theory you can consider them synonyms, and if you have a WordNet or thesaurus which has a data set of such of identifier names that you have pairs of identifiers that have these relationships, so antonyms, synonyms. In theory, they can, if you include them in representation learning, they can improve it. So we did not use them, but I think our results sort of highlight that if this notion of similarity, if these relationships are encapsulated while training, your embeddings might be better and you would see better improvement. So not for us, but I think this is what we have highlighted. If you use such tools, you might see actually an improvement. And this is what we wanted to highlight from this work.
Thank you very much. Jonathan, yes, feel free to follow up in case you want to follow up on that. We have another question from Fatima Fard. She says, very interesting work to begin with. Did you find any specific behaviors of the namings that can or cannot be captured using semantics or structure of the code? How useful are these code structures?
So in our work, so I haven't presented it in the presentation due to time, but in our paper, we actually do explore these some of these additional relationships. So we do explore abbreviations, opposites, synonyms, and something that we found was these tokens that have this additional identifiers with additional subtokens. So one example would be plurals primarily. So array list and array lists, identifier lists. So you have an S in the end, which this subtoken and in our case, even the path-based representation wasn't able to differentiate between because it sort of looked at the overlap of subtokens and it sort of like ranked them a bit higher. However, so as of right now, in our case, we weren't able to find a representation that actually was able to differentiate between them, that this is actually an array and this is one identifier and or one element. And we could not find any representation that was able to actually distinguish between them. So to answer the question, were there any specific behaviors? Yes, I think there are a few that we've actually highlighted. So abbreviations, opposite synonyms, and these additional subtokens, which is interesting. And I think this is something that the embeddings or representations should actually include as well.
That makes sense, yes. Have you explored the possibility of implementing this into some form of plugin for IDEs, for example, where if I name my variables in some way, your model could tell me, you know what, this is a more meaningful or a name that fits better in this context?
It's actually a pretty interesting thought. We did not do this exactly. However, what we did try was, can these individual representations be combined together to give you a better meaning? So instead of using just one representation, you combine them. So one of our research questions was, can each of these individual representations complement each other? Because we found that in some instances, path-based representations are actually better. In some instances, subtoken-based representations are better. So if you train a model that queries each of these representations, and then give you a more informed answer, that would actually outperform. And that is what we also showed, that we observed like 6 to 16% improvement in different tasks. So this is actually a pretty interesting line of research, which I think needs more investigation, where if you combine them, if you train, so instead of relying on just one, you combine multiple, that would actually show you more benefit.
Mm-hmm. Mm-hmm. In your, I'm still looking at the chat to see if there are any questions, but because we still have three minutes, I'll just take the opportunity to keep asking my questions. In your abstract, you have a sentence that says, so this may lead to fatal mistakes, such as, for example, in a refactoring tool. Could you elaborate a little bit on what you consider to be a fatal mistake? Is it something that would, because it's identifiers we're talking about, right? You might change the name, but how could it be fatal if it's just an? So it will be perhaps less understandable. But what do you mean by fatal?
I think we sort of had this line primarily to highlight the fact that semantics of the code itself would be different. So one example of this, if you have an automated recommendation, and this refactoring would be this this tool where you have this case where you have these additional subtokens, where you have a significant overlap between identifiers, and by just looking at them in an example such as if you use a string based distance metric, so Levenshtein distance, so list and list would be essentially the same because they have such a high overlap. But if you use one against in case of the other, you would see a completely different result. And also for these untyped languages, so JavaScript and Python, which wouldn't exactly check if this variable is the correct type, it would allow the code to actually be used. But in reality, if it's expecting an integer and instead you gave it a dictionary or a list, it would be completely different. And I think this is what we wanted to essentially highlight, where these existing approaches, where they have advantages, also have some disadvantages. And if you use them as they are, they would actually lead to some fatal results.
So in this sense, it would be because you are in the first place implementing a, let's say, unsafe refactoring, in the sense that you are not just changing the identifiers to make it look nicer or more, but you are somehow changing the AST of the program, so to say, right?
Sure.
Well, thank you very much. That's very interesting paper. Thank you, Mois, for all the answers and for not needing to go to Michael. And very nice presentation. Thank you very much. And I'll see everyone in the next Q&A session in 10 minutes.
Yeah.
Bye-bye.
Thank you.